Welcome back, and today we're going to be talking about the sine law, and my smart board's going funny again. Okay, so before we talked about the SOHCAHTOA and all that rules, and how that only works for right angle triangles only, but there's two laws that can be used to find missing side lengths and angles in any triangle. So it can be any single triangle, and as long as that triangle is labeled properly, you can use the sine law or the cosine law, and we're going to go over the sine law today. Pretty easy formula. Now, when we're using these formulas, the capital letters should represent angles, and the small letters should represent side lengths. The matching letters must be across from each other as well. So this is what we mean by labeled properly. So if I go ahead, so we have A, the capital letter A, that's a angle, and the small letter A is our side length. Okay, they have to be across from each other. So if we know, yep, those are across from each other, we're good on this one. Let's check B. So B's are across from each other. That's good. The capital B is on an angle, while the small b is on a side length. That's great. Then we check our last thing. So capital C is on an angle, small c is on a side length. Are they across from each other? Yes, they are. So we're all good. This is a properly labeled triangle. This means that we can use the sine law. What the sine law is that the sides of a triangle are proportional to the sides of the opposite angles. What this means is if this formula, so we have A over sine angle A is equal to B over sine B is equal to C over sine C. Okay. Or alternatively, we can also flip this. We can go sine A over sine length A, sine B over sine length B, sine C over sine length C. Note how they can be flipped back and forth. Okay. The only thing you can't do is something like A is over sine A is equal to B over sine B. This, not allowed. We can't just flip it like that. What we do on one side, we have to do to the other. Okay. So special note, although all three ratios are equal, we only use two at a time when solving problems. So for example, right here. Okay, so we don't use all three at a time, which makes this formula a lot more easier. If we show an example, find the value of x to the nearest tenth of a centimeter. Well, let's do this. What do we have? Well, we have, let's say, we're going to say, I'm going to label this angle A, angle B, angle C. Okay. What else do I have? Well, I have small c here then. I have small a here, small b right over here. What are my known values? I know angle C, and across from it, I also know side length C. I know angle B, and across from it, I don't know side length X. But because we have three known values and we have one unknown, this means we can solve it. I'm going to go ahead and write this out. So I have B. I don't know side length B. So I'm going to take B, and that's over sine B is equal to C over sine C. And the nice thing to note about this is if you're the one angle or labeling all these, I could have done A's, I could have done B's, I could have done C's anywhere, as long as they're labeled properly. Okay, so I have this. I'm going to replace everything that I know. So sine length B is my x. Sine B is going to be sine 45. I know sine length C, that's 35. And sine C is sine 39. Okay, so I have this equal to each other. We're going to isolate for x, which means we're going to go ahead and multiply the two together. Okay, so if I multiply this side by sine 45, then I multiply this side by sine 45 as well, which gives me my final value of x is equal to 35 times sine 45 over sine 39. And if I toss this into my calculator, because it says nearest tenth of a centimeter, it doesn't say exact value. If it said exact value, this question would be a lot more different. I have x is equal to 39.326, blah, 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 on and on and on. So if I'm approximating to the nearest tenth of a centimeter, I get x is equal to, roughly equal to 39.3 centimeters. So I just solved for that x value. Okay, repeating again. Let's see, this one says find the length of AC to the nearest meter. Okay, well, this one's labeled for us, so we can't really do much labeling. But we're gonna figure out what do we know? Okay, I have side length or angle A. I have 52, that's known. I have side length A here then. That's 45. So we know both of these values. That's good. That means we're gonna have to use this one. Now, they're asking for length of AC. Okay, well, I can do length of AC. Length of AC is right over here. So I'm going to label that my x. And we don't know that. Okay, but in order to find the value of x, we need to know angle B. We don't know that either. How do we solve that? Well, if you remember, in Math 10C, you probably learned about triangles. And triangles all add up to 180 degrees. So if we do 52 plus 118 plus the angle B, we should get 180 degrees. If we solve for this, we get that B is equal to 10 degrees. So my angle is 10 degrees here. Now I know the value of angle B, which means I can go ahead and solve this right here. Okay, I'm going to use my sine law again. This time I'm going to use A over sine A is equal to B over sine B. Replace all my values so I know sine length A is 45 over sine 52 is equal to X over sine 10. I'm going to skip a little step here, but if you solve for sine 10 here, you get B is equal to 45 times sine 10 over sine 52, okay, which means my B value is equal to 9.916, blah, 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 meters. That means our final side length B, or AC. Ooh, I don't know why I started using B there all of a sudden. Those should be X's. I'll replace that right now. X, X. So I know my side length X, or side length AC, is roughly equal to 10 meters. Okay, another example. This one kind of going backwards. This is find the value of theta to the nearest degree. Note it says nearest degree again. We don't care about exact values here. What information do we know? Okay, I know this and I know this. So those are both known. Okay, so I'm gonna go ahead and I want to label this C's again. So I'm going to do C and small c here. I also know this value. I don't know this value. Okay, so I'm going to go ahead and make this B and small b. And just for the sake of doing it, I'm going to label A and small a there. We don't know any of those values, so that means that's going to be useless here. Okay, now here we're going to solve again the similar way, and we're solving for angle theta. So we would do B over sine B is equal to C over sine C. Filling in all of our information, we have 14 over sine theta is equal to 10 over sine 43. If I'm solving for sine theta here, all I would do is multiply or cross multiplication, and I get sine 10, or oops, sine theta is equal to 14 times sine 43 over 10. which gives me sine theta is equal to 0.954 dot dot dot. And now here comes the little two-parter. We know that's what sine theta is equal to, but they want the angle. How do we do that? Well, toss that in your calculator again. So the inverse of sine of the theta is equal to the inverse sine of 954 dot dot dot. So you would put your answer in here, your full thing, and you get your theta is equal to 72.707 degrees, which means our final answer for theta is about equal to, and it says nearest degree, so it's equal to 73 degrees. Okay, so whenever you have an unknown angle, note it's going to take two steps. Okay, so you're going to cross multiply, divide, you're going to do all your stuff to solve for it, and then you have to use the inverse sign in order to get the angle. All right, now we get into something called the ambiguous case of sine law. Okay, sometimes when you are given two sides and an angle opposite one of the sides, so you're given a side, and angle, it's possible to draw two triangles, one acute and one obtuse triangle. This is known as the ambiguous case. Okay, so for example, you can draw an acute or an obtuse triangle, okay, that have both of the same things. So if we're given a degree, so let's say we're given 30 degrees and we're given the 10. We're also given a 16 degree. Well, you can actually do two things with that. I can do my 30 degrees here, and that's going over, this is a 10 side length, and then 16 side length here. But I can also have the same thing with 30 degrees, 10 here, 16 here. But notice how the B's are completely different. Our side length B is completely different. Our side length C is completely different. So because of this, this is what we call an ambiguous case. We don't know. We're given two side lengths and an angle. We don't know what this is. Okay? So for example, if we go and we solve for this, the case of the dead meteorologist, where the weather balloon transmits and there's a tornado 15 kilometers from the balloon. Okay, so we're given a side. The balloon is 25 kilometers from the meteorologist. We're given another side. And the balloon is at a 20-degree angle from the meteorologist. We're given an angle. We're given a side angle. Okay, so this means we're going to have two cases. I'm going to go ahead and write all my cases down. So I'm going to say my meteorologist is A, which means our side length here is A. My tornado can be C, and my balloon is B, and side length B. Okay, if I go ahead and fill this out, I know my meteorologist is at a 20-degree angle from here to the balloon. I know that side length C is 25 kilometers. And I know that tornado is 15 kilometers from the balloon. Okay, what is this asking for? Calculate the distance between the meteorologist and the tornado. So it's asking for side length B here. Okay, I have all the information I need to solve this, but if we look over here, there's another case that the same thing could happen. So if I label them the exact same thing, uh, A, small b, C, small a, big B. I go ahead and label this, and I put the exact same angles in. So I have 30 degrees there. I know that C is 25 kilometers. A is 15 kilometers. Notice how I can still get the same values for my sides, lengths, and my angles, but they're two completely different triangles. In the first one, he's really far from the tornado. He probably doesn't have too much worry. In the second one, it looks like the tornado is going to hit him any second. Okay, let's calculate this, okay? We're going to go off the meteorologist calculations, which means we're going to go off the first part. We follow the same thing. Well, we're solving for B here. We're solving for B, which means we're going to be doing, let's see, okay. Whoops, sorry. We're solving for side length B, but we don't know angle B. That means we can't use that. This is going to be a two-parter. It's going to be a little bit harder. What we do know is we know angle A and we know side length A. We know this. What else do we know? Well, we know side length C. That means we don't know what angle C is. So we're going to have to go ahead and use this. And we're going to have to solve for angle C. So I'm just going to go ahead and fill this all in. So 15 over sine 20 is equal to 25 over sine C. From here, I get sine C is equal to, I'm just going to skip the calculation. I'm sure you can do it. 570. And if I use the inverse sine, so I know that my angle of C is going to be the inverse sine of 0.570. I get that this is equal to about 34.752. And I also know, just off this, I know that this is an acute triangle. Okay, so because there's an acute triangle here, I know that there's also an obtuse angle, or obtuse solution. Okay, so I'm gonna bring that right here, and I know that sine is positive in Q1 and Q2. So that means there's another solution. Be another solution. Okay, which means the other solution would be that if we do angle C, we're going to do the opposite. So we're going to doing our 180 minus the same reference angle, 34.752 dot dot dot. That means we have another solution where it's 145.247 degrees. And this is our obtuse triangle solution. So we kind of just skip a step of having to calculate that by just working off our reference angles, because we know that sine is positive in Q1 and Q2. Okay, so working off this, do I have space down there? Nope, I'm gonna have to write really small, but that's okay. I have my reference angle of C, and now because we have that, we're gonna solve for our angle of B. To solve for that, all you do is 180 minus 20 minus 34.752, and angle B we get 125.247. Okay. So if I go ahead and I were to solve this all out, so A over sine A is equal to B over sine B. I think you all are pretty good at this now, so I'm just going to skip ahead to the answer. I get something that B is roughly equal to 36 kilometers. Hopefully you got that. So the meteorologist in this case is okay. He's pretty safe, 36 kilometers away. But let's check the alternate solution. If this was the other way, again, you would do the same thing. So you do A over sine A is equal to B over sine B. But in this case, making sure to use our other angle here. So if we calculate our obtuse angle, if we go ahead and we do angle B for this case, and we do 180 minus 30 minus 145.2 dot 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 752, we get this is equal to 14.752 degrees. That's really small. If we go ahead and fill this in using that for B, okay, what we get is our side length B is about 11 kilometers away. Okay. And in this case, the meteorologist is not okay. He would not be fine at all. He would definitely feel that tornado. Okay. One more example of an ambiguous case. So I'm gonna go ahead and draw the two cases for you. So in our first case, we have angle AB or triangle ABC with the angle 52, side length B, and side length A. So we know that maybe there's two possible measures for this angle C. Okay. In the first case, I'm just going to draw my standard acute triangle. And in my second case, I have my obtuse triangle. I'm just drawing basic triangles here. So if I fill everything in, A, B, B, C, C, go ahead, fill everything out. So I know this is 52 degrees. I know that A is equal to 10 centimeters, and I know that side length B is equal to 12 centimeters. Okay. In our obtuse case, following this exact same thing, A, C, B, C, A, B, I again put in my same angle, 52 degrees, but over here, we have the same thing, so 10 centimeters, and B is also 12 centimeters. Okay, now note I didn't draw these properly, but what you would do is you use your sine law and figure out what is the angle of B. Okay, what you end up getting is if you use your sine law and solve for B here, you get that the angle B is equal to 71.016 uh, degrees. This makes it acute. Okay. Likewise, if I go and I do the other one, or if I do angle B, which is the reference angle minus that, we get 108.983. And in this case, this one is obtuse. So right off the bat, I have two different angles, and they are ambiguous. We don't know which one. Okay. So if you go ahead and you were to actually solve for this, I won't do it here because this video is already quite long, but I want you to give it a try. You should get that your side length C is equal to 10.640 in the acute scenario. And in the obtuse scenario, we get that C, side length C is equal to 4.134 centimeters. Okay, so our final solution would look something like uh, angle C is roughly equal to 57 degrees or 19 degrees, and side length C, so small c, is roughly equal to 10.6 centimeters or 4.1 centimeters based on what we got here. Okay, if you are all okay with that, that is all for today. Give that a try, see if you understand it. Bye bye. Bye bye.